In this video, we are going to talk about the negative binomial distribution. This is our overview slide, which we'll spend about 5 minutes going over before going over each topic in more detail and with more examples. The negative binomial distribution is the probability of observing the kth success on the nth trial. So probability of the kth success on the nth trial, or probability that the nth trial yields the kth success, is equal to n minus 1 choose k minus 1, p to the k, 1 minus p, raised to the n minus k. A note which we'll take a closer look at in the main part of our video: if p is small, we expect n to be large. And last, the n minus k and the k minus 1 comes from the fact that the last trial is a success. Again, we'll look at this closer in the main part of our video. There are 4 conditions for a negative binomial. First, the trials must be independent. Each trial outcome be classified as a success or failure. The probability of success p is the same for each trial. In other words, these 3 conditions make it a Bernoulli trial. And finally, the last trial must be a success. The negative binomial and the binomial distributions are very similar. One, they both rely on Bernoulli trials. Here, again, the negative binomial is the probability of the kth success on the nth trial, whereas the binomial is the probability of observing exactly k successes in n independent trials. So here, you know how many successes you want, and you're asking how many trials will it take to get k successes. Here, you know how many trials you have. You have n trials, and then you're counting the successes. So they're just sort of the opposite of which one they're trying to predict and which one is known. The probability of k successes in n trials, that's the binomial, is n choose k, p to the k, 1 minus p to the n minus k. You can see this formula is very similar to the negative binomial. The biggest difference is this choose, n choose k versus n minus 1, choose k minus 1. And the reason why this part here has a minus 1 is the fact that the last trial is a success. So when we're arranging our successes and failures, there's one less success to arrange. It goes at the end. We'll take a closer look at that as well. And as I had mentioned, in the binomial case, we have a fixed number of trials and we count the number of successes. And the negative binomial, we don't know how many trials we will have, but we want a fixed number of successes. So it's just opposite. And also in the negative binomial, we require the last observation to be a success. Our main example that we're going to go over is each day a high school football coach tells the star kicker Brian that he can go home after he successfully kicks 4 35-yard field goals. Suppose each kick has a probability p of being successful. What is the probability it takes 6 tries to get the 4th goal if p equals 0.8? Here, the probability of a goal or a success is equal to 0.8. We want to know the probability it takes 6 trials, so n equals 6. And we want the 4th goal, so we definitely want 4 successes. So it's the number of trials that varies, but we want to know that the probability n equals 6. We know we want 4 successes, so this is what makes it a negative binomial. So we plug it into our formula, n minus 1, that's 6 minus 1, choose k minus 1, that's 4 minus 1, probability of a success raised to the number of successes, 4, probability of failure, which is just 1 minus probability of success, times the number of failures. Well, if we have 6 tries and 4 successes, that must mean we had 2 failures. So here we have 5 choose 3, 0.8 to the 4th, 0.2 squared, which gives us a 16.34%. And that concludes our overview, so we're going to go back up and take a closer look at the negative binomial distribution. Here are our notes about negative binomial distribution, a reminder that that's the probability of observing the kth success on the nth trial. And this is here for your reference. And we're going to use this example of the field goal kicker Brian to motivate our discussion. So each day, a high school football coach tells the star kicker Brian that he can go home after he successfully kicks 4 35-yard field goals. Suppose each kick has probability P of being successful. Now, if P is small, let's say it's close to 0.1 or 10%, 10% of the time he'll make that field goal. Would we expect Brian to need many attempts before he successfully kicks his 4th field goal? So again, we want his 4th field goal to take n attempts. We want 4 successes. How many attempts does it take? This is what makes it negative binomial. And, if any one given kick has a small chance of being a goal, then yeah, we would expect it would take a while before he gets 4. So if P is small, we expect n to be large. And this is this note here that is kind of useful to keep in mind, right? If any one attempt has a small chance of being successful, then if we want multiple successes, n is going to be large. It's going to take many times to try before we actually get 4 field goals. And then next we have these 4 conditions for a negative binomial just to help you recognize when the problem needs this formula here or this approach here. 1, we have independent trials. Each trial outcome can be classified as a success or failure. Probability of success P is the same for each trial. These first 3 conditions, these are equivalent to saying you have Bernoulli trials. And we had talked about Bernoulli trials in our previous video. So we're talking about Bernoulli trials, and then this last condition, the last trial must be a success because that's the probability of observing k successes on exactly the nth trial. And again, in this problem, the k successes, well, those are the 4 successful field goals. And n, we're counting how many attempts he needs to take until he finally gets 4 field goals. Our next question is, at yesterday's practice, it took Brian only 6 tries to get his 4th field goal. Write out each possible sequence of kicks. So for this, I'm just going to use some notation. F is a failed attempt. S is a success. In this case, we said that n is equal to 6. So after 6 tries, he got 4 field goals. I should probably put k is equal to 4. So we want to write out each possible sequence of kicks. So we have 4 successes, which means he had 6 kicks, which means he has 6 minus 4, or 2 failures. So this problem is like arranging 4 S's and 2 F's. The S's stand for success, the F's stand for failures. And what I'm going to mention, this arrangement of S's and F's, that's something we talked about with Bernoulli trials. We said that n choose k is the number of ways to arrange k successes and n minus k failures. So in this case, k would be equal to 4, and n minus k, 6 minus 4, is equal to 2 failures, which is what we had noted before. But there is one other thing we have to remember. For the negative binomial distribution, the last kick is a success. So this is important. So when we have all our sequences of S's and F's, there's going to be one less success to arrange because one of the successes is automatically going to the end. So we're going to arrange 3 S's and 2 F's. So we're going to have 3 plus 2, that's 5, with the 3 S's. Again, 5 choose 3 is the number of ways to arrange 3 successes, and n minus k, that's 2 failures. So we work this out and we get 10 ways. And again here, our formula was n minus 1, right? So we didn't use n equals 6, we used n equals 5 because we have one less s to arrange. And then here on the bottom, the ways to arrange k successes. Again, we don't have 4 successes now to arrange because one of them automatically gets put to the end. So we're only arranging k minus 1 or 3 successes. So there are 10 ways to do this. I listed our ways of arranging 3 successes, 2 failures. And then at the very end, I put our last success. So that will be our fourth success on all of our 10 possible ways of having a sequence of 6 tries with 4 successes. Now we might want to know the probability of this sequence, F, F, S, 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 S. That's this last sequence down here. So our 2 failures at the beginning and then 3 successes at the end, and the probability is equal to 0.8. So that's going to be 2 failures. So it's the probability of failure is 1 minus 0.8, and there are 2 of them, so we square that. And then we have 4 successes. So probability of success, we have 4 of them, so we raise that to the 4th. And our final answer is 0.0164. That is 1.64%. Now we know the probability of this last outcome here. We want to know what is the probability it takes 6 tries to get the 4th goal if p equals 0.8. And that's the probability of our sequences of kicks are, and I listed all 10 of them, success, S, S, F, F, or we could have this next possibility that we have a success followed by a success, followed by a failure, followed by a success, followed by a failure, and then of course our last success. I didn't always put the blue S's here, but remember there's a success at the end. Maybe I should write them in. And then I just went down the list of all 10. So these are the different ways of having 4 successes, 2 failures. In other words, 4 successes and 6 tries. So we want that probability. Since these are independent events, this OR becomes a plus. So it's the probability of each of these individual possibilities. And I tried to add the little S's, the success at the end. So it turns out all of these, if you look at them, they're going to be symmetric. In other words, we're going to be multiplying our 0.2, our 2 failures, twice, and we're going to be multiplying our 4 successes 4 times. So all of these are going to be the same probability, which is 0.0164. There's 10 of them, so we multiply by 10. So our final probability is going to be 16.4%. And so actually I needed to be more careful. These blue S's I absolutely needed because I needed to make sure I had my 4 successes. So I needed to have the 0.8 times 4. Your book says the negative binomial distribution requires that each kick attempted by Brian is independent. Do you think it's reasonable to suggest that each kick attempt is independent? And I'm just going to go with saying, that's hard to say. Personally, I don't think they're independent because if I were having a bad day, then I'm not going to make it. Or, my first kick is going to be bad, my second kick is going to be, all of them are going to lower my probability if for whatever reason I have a bad day. Or maybe even psychologically, if I'm doing well, maybe I'm on a streak. Psychologically, maybe that'll help me keep making kicks. But your book says there is evidence for professional kickers that each kick does seem to be independent of the next. I guess they're not, maybe they don't play when they have bad days. And also psychologically, they put away any failures or successes they've had and just kind of keep at it. They're very consistent. Okay, we're going to keep with Brian here. When he was at 0.1%, I felt kind of bad, but now his probability is 0.8. So what's the probability Brian will kick his 4th field goal within 5 attempts? So I like writing things down. My K equals 4. I'm looking for 4 successes. Last kick is a success. So just to note that K minus 1 over here is equal to 3. So 5 attempts, within 5 attempts, that means he could have n equals 5 or n equals 4. He can't have n equals 3 because he needs at least 4 field goals. So he needs to kick at least 4 times. So we're talking about what's the probability that he gets his 4th success on the 4th or 5th trial. So just writing that, K equals 4 successes and N equals 4 or 5 attempts. Again, the last attempt needs to be a success. So here, breaking this down, he can either have 4 successes and 4 attempts, so K equals 4 and N equals 4, or he can have 4 successes and 5 attempts, K equals 4 and N equals 5. So I can plug into my formula, N minus 1. So for 4 successes and 4 attempts, N minus 1, that's 4 minus 1. And then over K minus 1, that's also 4 minus 1. Then I have my probability of success, and I have 4 successes, so I raise it to the 4th. My probability of failure, which is just 1 minus probability of success, that's 0.2. But I have no failures, so that's just raised to the 0. Remember, anything raised to the 0 power is just 1. Then next, I'm going to look at my 4 successes and 5 attempts. So K equals 4, N equals 5. So N minus 1 is 5 minus 1. My K minus 1 is 4 minus 1. My probability of success times, or raised to the number of successes, which is 4. My probability of failure raised to the number of failures. Well, if I have 5 tries and only 4 successes, that means I had 1 failure. I can then do all the calculations here, and I'll get 0.74, or 74%. Next, I want to compare my binomial distribution to my negative binomial distribution. So I kept my notes for the negative binomial distribution here, and I added notes from our last video about the binomial distribution, which said suppose the probability of a single trial being a success is P, then the probability of observing exactly K successes and N independent trials is given by N choose K. Again, that's the number of ways of arranging K successes and N minus K failures. Probability of success raised to the number of successes. Probability of failure, which is just 1 minus probability of success, raised to the number of failures, which is N minus K. So in the binomial case, that's this one right here, we typically have a fixed number of trials, and we're counting the number of successes. In the negative binomial, we examine how many trials it takes to observe a fixed number of successes. So again, binomial, we fix the number of trials. Negative binomial, we fix the number of successes. Over here, binomial, if you fix the number of trials, then you're counting the successes. In negative binomial, if you fix the number of successes, you're counting how many trials. That seems straightforward enough, but sometimes the problems, you really have to give it some thought. So let's do an example. Our example, on 70% of days, a hospital admits at least 1 heart attack patient. It'd be nice if these were like happy statistics, but whatever. 70%, 1 heart attack patient on a day. On 30% of the days, no heart attack patients are admitted. So we're going to have a number of questions, and we want to identify each case as binomial or negative binomial, and then we want to compute the probability. And our 3 questions are: 1, probability the hospital will admit a heart attack patient on exactly 3 days this week. Probability the second day with a heart attack patient will be the 4th day of the week. Probability the 5th day of next month will be the 1st day with a heart attack patient. And before we consider these 3 things, I'm just going to write what we know. Probability at least 1 heart attack patient that day is 70%, and we call that a success. And again, I put success in quotes because you probably want days with no heart attack patients. But just because this is given, P is given as 0.7, we're going to consider that a success. Our first question, the probability the hospital will admit a heart attack patient on exactly 3 days this week. So we want to know, are we counting the number of successes, or are we trying to figure out what trial number gives us a given number of successes? So remember, a success is a day with a heart patient. And I hate saying that's a successful day, but that's just how it's defined. A success is a day with a heart patient. We want to know the probability there are 3 days with a heart patient. So it looks to me like we're counting successes, 3 successes in 7 days, and 7 days because we're talking about a week. So it looks like we have a fixed number of trials. We have 7 days and then we're counting the number of days with a heart attack patient. And we want to know the probability that it's 3 days, that it's not 1 day or 2 days, but it's 3 days that we have heart attack patients. So in other words, it's binomial. We have 7 trials, 7 days, and we're saying what's the probability we have 3 successes. So this is how we would set up the answer to that problem. It's going to be 7, choose 3. 0.7 is our probability raised to the number of successes, which is 3. 1 minus 0.7, which is probability of failure. And then if there are 7 days and we only have 3 successes, that must mean we have 4 days where we're not successful. So this is the answer. Again, a binomial distribution, because we're trying to figure out how many successes in a given number of days. The next problem, probability the second day with a heart attack patient will be the 4th day of the week. And I'm going to encourage you to try to pause the video and think about this on your own, because it's easy enough to follow what I say, but to come up with the reasoning, it takes a little bit of thought. So pause the video and then come back. Okay, probability the second day with a heart attack patient will be the 4th day of the week. So it's like we're looking for 2 successes the second day with a heart attack patient. And we're predicting what day of the week that will be, how many trials it will take. So we're saying the second day with a heart attack patient, that's 2 successes by day 4. So this is a negative binomial distribution with k equals 2, that's the number of successes. Number of trials is equal to 4. So using our negative binomial, we're going to have n minus 1, which is 3. Choose k minus 1, which is 2 minus 1, which is 1. We have our probability of success, 0.7, times the number of successes, which is 2, or raised to the 2. And then our probability of failure, which is 1 minus 0.7, which is 0.3, raised to the number of failures. So if we have 4 trials and only 2 successes, that means we had 2 failures. So this is the answer to part B. Finally, we have probability the 5th day of next month will be the 1st day with a heart attack patient. Again, I would pause this video and give it a try. And just think, when we're counting the number of days, start from the 1st day of the month. So pause the video, give it some thought, come back. So this here, 1st day with a heart attack patient, it looks like we're looking what day we get a success, our first success. So in other words, n equals 5 days before our first success, which sounds like a negative binomial with k equals 1, our first success, or just our 1 success, and we're looking for the probability that the number of trials or number of days is equal to 5. So plugging that into our formula, the 5 minus 1 is 4, choose 1 minus 1 is 0, and that's okay, because remember 0 factorial is just equal to 1. We have our 0.7 probability of success times the number of successes, just 1. And then 0.3 is probability of failure, or 1 minus 0.7, minus the number of failures. 5 trials, 5 days before we get our first success. So that means there's 4 failures. So again, these problems seem more difficult than when you look at the description of binomial and negative binomial distribution, because when you look at negative binomial, it seems very clear that you're looking for k successes, so you want to know the nth trial. Binomial, it knows you have independent trials and you're looking for k successes, but here it seems like they're giving you both, and they absolutely are, because they're asking you the probability the nth trial leads to a k success, or the probability that, where's binomial? There are k successes and n trials. So they do give you both, but what you have to do is get to what is considered a success, or what are you looking for? So the thing you want to determine is, what are you looking for? Are you looking for the successes, or when the successes happen. So you do want to know what is considered a success. Let's look at the first problem. Probability the hospital will admit a heart attack patient on exactly 3 days this week. So the probability, what is it that we're looking for? The hospital will admit a heart attack patient. And then we're saying 3 days this week. So we have a given number of days that are our trial days. So our 7 days is the number of trials. And we're looking to see if we have exactly 3 days that we admit a heart attack patient. So our success is our 3 days with heart attack patients. 3 successes in 7 days or 1 week. Let's look at the second one. Probability the second day with a heart attack patient will be on the 4th day of the week. So the probability the second day, so we're counting. So I'm trying to look at what the probability is looking for. It's the second day with a heart attack patient. So that's kind of like what we're counting then, right? We're counting the number of days or number of days with a heart attack patient. And we're saying that'll be on the 4th day of the week. In other words, the 4th, that's our number of trials. So this is a number of trials, the 4. Second day with a heart attack patient. So in other words, 2 successes on day 4. So that makes it a negative binomial. Finally, probability the 5th day of next month will be the first day with a heart attack patient. We're looking for probability of a 5th day. So it sounds like we're counting the number of days or figuring out how many days. And this is what we're looking for, the first day with a heart attack patient. First day with a heart attack patient. And we're saying, will that be the 5th day? So the number of trials until we get to the first day with a heart attack patient, is the number of trials going to be 5? So that's n equals 5 days before the first success. I hope that helps you, but one thing that really helps me is just to kind of try to break it down or say it in different ways until it sounds like the description of a negative binomial or binomial distribution. To review what we've gone over, we talked today about the negative binomial distribution, which is the probability of observing the kth success on the nth trial. And we have this formula here for the probability of the k success on the nth trial, or the nth trial yielding the k success, is equal to n minus 1, choose k minus 1, p to the k, 1 minus p to the n minus k. And if p is small, we expect n to be large, because if the probability of 1 success is small, then to have k successes is going to be small as well. And so we're going to have to try many times. There are 4 conditions for the negative binomial. The first 3 amounts to it's a Bernoulli trial. And then the last trial must be a success. We talked about binomial versus negative binomial. So the binomial distribution is the probability of observing k successes and n independent trials. And we have this formula here for probability of k successes and n trials is n choose k, p to the k, 1 minus p raised to the n minus k. So in the binomial case, we typically have a fixed number of trials and count the number of successes. In negative binomial, it's the opposite. We count the number of trials it takes to observe a fixed number of successes. And our example was, each day a high school football coach tells the star kicker Brian that he can go home after he successfully kicks 4 35-yard field goals. Suppose each kick has a probability p of being successful. What's the probability it takes 6 tries to get the 4th goal if p equals 0.8? So the probability of goal is 0.8. The number of tries, we said probability it takes 6 tries to get the 4th goal, so that's 4 successes. So plugging into our formula for negative binomial, we have 6 minus 1, choose 4 minus 1, 0.8 to the 4, and 1 minus 0.8 squared, and that will give us 16.34%. And that's the end of this video. Thank you for watching.